السلام عليكم ورحمة الله تعالى وبركاته. I'm Salma Al-Mahdi. Today we are going to discuss the structure and function of hemoglobin. Our objectives are to describe the different levels of hemoglobin structure, to compare and contrast hemoglobin and myoglobin, list and differentiate variants of hemoglobin, to discuss the role of heme and ion in oxygen binding, to illustrate the oxygen dissociation curve and factors that affect oxygen affinity, define what is meant by Bohr effect and its physiological significance, describe common hemoglobinopathies. Hemoglobin and myoglobin both are proteins that maintain an oxygen supply for oxidative metabolism. Both of them illustrate protein structure-function relationship, and they both illustrate molecular bases of genetic diseases. So when we study hemoglobin, we will have a practical example of how structure dictates function, or how structure is related to function in biochemistry, and we are going to illustrate some examples of genetic diseases, and we are going to discuss its molecular basis in relation to hemoglobin. Both hemoglobin and myoglobin contain heme as a prophetic group. You know that a functional whole protein is a hollow protein. It consists of two parts, an apoprotein, which is the pure protein part, and a prosthetic group, which is a non-protein part. So in a functioning hemoglobin or myoglobin, the non-protein part, the prosthetic group, is heme. Heme and ion together confers the ability to store and transport oxygen. So heme and ion are both important for the function of myoglobin and hemoglobin. This is a hemoglobin molecule, and these are four prosthetic groups, heme groups. So we are starting with heme. Heme is, as we said, a non-protein prosthetic group. It consists of protoporphyrin, which is organic part made up of four pyrrole rings, so it is a tetrapyrrole linked by methylene bridges. In addition to ion, present in the ferrous state, inorganic part resides at its center. Oxidation of ferrous to ferric destroys the biologic function, so we need the ion of hemoglobin or myoglobin to always be in the ferrous state. This is the four pyrrole rings linked by methylene bridges, and in the center we have ion in the ferrous state. The conjugated double bonds absorb visible light and give the characteristic red color of blood or any compound that contains double bonds. In addition to the four nitrogen atoms, ferrous forms also two additional bonds on either side of the heme. So if you look in the three-dimensional configuration, these ends represent the four pyrrole rings linked to ferrous in the center. Additionally, ferrous has two more additional binding sites called the fifth and sixth coordination positions, which are perpendicular to the plane of the rings. So the four tetrapyrrole rings are present on one plane. If you look at them from the side, you can understand them as being corners of a sheet of paper. So they are present on the same plane horizontally. Perpendicular to them at 90 degrees, there is additional two binding sites, the fifth and sixth coordination positions. So we start by myoglobin because it is smaller and it will help us in understanding the more complex structure of hemoglobin. Myoglobin is considered the heme protein of red muscle. Notice here we have written heme separate from the word protein. Heme protein means that it's a protein that contains heme. Hemoprotein with an O that connects the two parts of the word is our hemoprotein of the blood. So myoglobin is a heme protein of red muscle. It is present in red muscle. It is apropular, so it is shape is globular shape. It is monomeric. It consists of one polypeptide chain. Its function in storing oxygen against oxygen deprivation, strenuous exercise. So it provides oxygen for muscles that are exercising, particularly a heavy form of exercise. It contains, structure-wise, it contains 153 amino acids as its primary structure. Remember, the primary structure is the number and sequence of amino acids, and if there is any disulfide bonds that will be marked. So primary structure of hemoglobin is a series of amino acids, 153 amino acids. Regarding its secondary structure, it is rich in alpha helices. Regarding its tertiary structure, it falls into a compact molecular structure. So the three-dimensional structure is the molecular structure. The tertiary level is the farthest that hemoglobin can reach because it is a single polypeptide. It's a monomer. It cannot have a quaternary structure, unlike hemoglobin. So this is our hemoglobin. These are the helices that represents the secondary structure. These helices are linked, of course, by loops, which are also secondary structure. And this is the heme here in the middle, and this is the ion molecule. Counting from the N-terminus to the carboxy terminus of the myoglobin, you can count 8 alpha helices. They are termed A, B, C, up to H. Typically, the surface is made of polar residues because they will be facing water and with the mostly hydrophilic environment in the body, and the interior of the molecule will be made of non-polar residues. We mean non-polar amino acids, of course, except two histidines. So in the core, although the majority will be non-polar amino acids, we have two exceptions that are present. We have two polar amino acids present called histidine E7 and histidine F8. E7 and F8, the E and F refers to the helices in which these amino acids are present. We said the helices are from A to H. And 7 or 8 is the number of the histidine. So E7, histidine E7, is the seventh residue in helix A. So if we took helix A and we count it from 1 to 7, the seventh residue will be histidine. Likewise in F8. And these are important for the function, of course, of both hemoglobin and hemoglobin. We will come to them shortly. Heme of hemoglobin lies in crevice between helices E and F that we have just mentioned. The fifth coordination position of the ion, of the ferrous ion in hemoglobin is linked to N of the histidine F8, which is called the proximal histidine, and the histidine E7, which is called the distal histidine, lies opposite to histidine F, but is not linked to the hemoglobin. The sixth coordination position of ferrous ion finds oxygen. It will be, of course, free if if there is no oxygen, the hemoglobin is deoxygenated. So if you look here, this represents the helices, lettered capital letters in English, capital letters, helix A, helix AB, B, and so on. So we are concerned with helix F and helix E. As we said, they contain two histidines that are polar residues that are embedded within the core of the myoglobin molecule, and of course also in the hemoglobin molecule later on. And they are related to the function. They are linked closely to the tetrabinary ring of and the ion. If you look here to right, this is a schematic representation. This here represents the plane of the molecule, and this is ferrous in the middle. This is to show you that the fifth and sixth position. The fifth position here of the fourth positions, of course, are all for the four tetrabinary rings around the tetrabinary ring. The fifth position of ferrous ion is occupied by N of the histidine, particularly the proximal histidine. The fifth position of binding to ferrous ion will be occupied by the molecule of oxygen. The sixth coordination position is outside the plane of this figure. This is another representation. This are the four ends of the tetraviral rings. This is ferrous in the middle. The fifth coordination position is linked to the end of the proximal histidine, F8. The sixth position here is free because it is not yet oxygenated, and this is the distal histidine E7. Oxygen comes and binds to the sixth position of ferrous, and the distal histidine remains free. So how myoglobin is oxygenated? In unoxygenated myoglobin, ferrous lies at a distance of 0.3 angstrom, that is 0.03 nanometer outside the plane of the membrane. With oxygenation, oxygen of course occupies the sixth coordination position, as we said. This will lead to movement of the ferrous ion to within 0.01 angstrom or 0.01 nanometer of the plane of the heme. So oxygenation or binding of oxygen to the sixth coordination position moves the ferrous molecule closer to the plane of the heme. This is the plane of the porphyrin ring, or the tetraviral ring. This is the ferrous ion. It lies outside of the plane of the porphyrin, and this is of course this is the rest of the helix F, and this is the proximal histidine, which is linked by his nitrogen to the fifth coordination position of the ferrous molecule. With oxygenation, here oxygen binds to the sixth coordination position. The molecule is pulled within the, now it is at the same level of the, almost at the same level of the of the porphyrin ring. This small movement is very crucial to the function of the myoglobin molecule as a whole. Heme protein and hemoglobin. Hemoglobin is the heme protein of erythrocytes of the red blood cell. It is tetrameric, so it consists of four protein or polypeptide chains. The overall shape of it is globular, similar to myoglobin. The function is transportation instead of storing, as we said in myoglobin. Hemoglobin transports oxygen to tissues and carbon dioxide to lungs. The function of hemoglobin can be interrupted by carbon monoxide, which is a poison to the function of hemoglobin. Why? Because carbon monoxide binds tightly to hemoglobin, which inverts the Bohr effect and will reduce oxygen unloading to tissues. At the end of the discussion, we will talk about Bohr effect, and we will know what is it and why it is important for oxygen delivery. Carbon monoxide cannot be seen, cannot be smelled, cannot be heard, so it is very serious type of poisoning, but it can be stopped by having, for example, carbon monoxide detectors in the home or in the workplace. Regarding the structure of hemoglobin, as we said, it is a tetra polypeptide, tetramer, but the tetramer is folded into two pairs, and each pair contains two different polypeptide subunits. Which signifies the variance, at least the normal variance of hemoglobin. So when there are two alpha chains linked to two beta chains, this represents hemoglobin A, which is our normal adult hemoglobin. We have also a minor adult hemoglobin that contains two alphas and two deltas. Two alphas and two gammas represents fetal hemoglobin, the hemoglobin that is functioning is a fetal period of life. Two alphas and two S hemoglobins is an abnormal variant of hemoglobin, that is sickle hemoglobin. Two sigmas and two epsilons are GOR1 hemoglobin, and two alphas and two epsilons are GOR2. There is a 2 here is missing. Two sigmas and two gammas is Portland hemoglobin. These three are called embryonic hemoglobins that appear early on during the embryonic life, and they will disappear before the fetus is born. And this is a representation of the four main variants: hemoglobin A, 2 alphas, 2 betas, 2 alphas, 2 deltas, 2 alphas, 2 gammas, 2 alphas, 2 second hemoglobin or S hemoglobin. And this is to show you their timeline or chronological order of appearance and disappearance. So starting from 0 age up to 6 months, and this is birth year. So this here represents the fetal life, and early on this is embryonic life. And these are the chains. So alpha chain is present almost all the time because it is needed for the variant forms of hemoglobin. Our adult hemoglobin, the one here, it contains 2 alphas and 2 betas, so this one continues throughout our adult lives. Our minor hemoglobin here continues for a minor, it will be represent a minor percentage of our adult hemoglobin. The major one will be hemoglobin A1, this one here. The fetal hemoglobin, for example, 2 alphas and 2 gamma chains, it will continue throughout the fetal life, but after birth, the gamma chain will be start to decline because fetal hemoglobin is no longer needed, and the child will start to germinate, will start to assume the adult hemoglobin. So as you can see here, the beta chain is on the rise. This here represents the epsilon and sigma chains of embryonic government and hemoglobin. They are present for less than 3 months of the early fetal life. They disappear after that. A secondary tertiary structure of hemoglobin resembles myoglobin, but the trimeric structure of hemoglobin shows cooperative interactions between the subunits. That is to say, the four polypeptide chains of hemoglobin cooperate in performing the function which is oxygen transport. Of course, this is not present in myoglobin because it is a single chain. So cooperation is a characteristic of hemoglobin that's not present in myoglobin. Myoglobin and the beta polypeptide of hemoglobin. So the beta polypeptide or the beta chain of hemoglobin resembles myoglobin. Both of them are single chains. They have different amino acids and type and number. So they similar, but the differences include differences in the primary structure, that is the number and sequence of amino acids. However, they have similar heme location, they have similar egg helices, and they have amino acids are almost comparable bigger, so they have an almost similar secondary structure. The alpha polypeptide also resembles myoglobin but has 7 helices instead of 8. Oxygenation of hemoglobin is similar to that of myoglobin. Ferrous of the oxyhemoglobin lies at about 0.6 nanometer outside the plane of the heme, and with oxygenation, ferrous moves into the plane of the porphyrin, and the motion is transmitted to the proximal histidine F8 of the residue attached to it. So when there is no oxygen, ferrous lies outside the plane of the porphyrin ring, and with oxygenation, binding of oxygen to the 6th coordination position, ion is now moved closer to the plane of the ring, and with that movement, ion pulls the proximal histidine is with it, and the proximal histidine, of course, will pull the whole chain with it. So it is as if it is somebody is pulling somebody, and the pulling continues to the next person. So ferrous is pulled to the plane, it pulls with it the N-nitrogen, it will pulls with it the whole proximal histidine, it will pull with it the polypeptide, the whole polypeptide chain. Oxygenation of hemoglobin requires rupturing of salt bonds between the four separates, and this will of course alter the secondary, the tertiary, and the quaternary structure of hemoglobin. So the mere binding of oxygen leads to large conformational change within the hemoglobin molecule. These are the salt or electrostatic interactions we are talking about. Salt means that salt bonds or salt bridges means that it is formed between positive and negative entities. So between aspartate here, a negatively charged amino acid, and histidine here, a positively charged polar amino acid, between the negatively charged carboxyl group and a positively charged calcium residue, and so on. So all of this shown in red, the salt bridges, will be broken due to the movement or the pulling of the ion into the positions. That spironomical movement will rupture all these bonds shown in red. One pair of receipt is present as two pairs. One pair of alpha beta will rotate 15 degrees relative to the other alpha beta pair. So we call it movement from the top T form to a relaxed R form or R state. This here shown here is the third form, sort of compact or restricted representation of hemoglobin molecule, whereby this alpha and beta pair, alpha 1, beta 1 pair, shown in white, is opposite to the beta 1, beta 2, alpha 2 pair, with binding of oxygen and the transmission of motion. The two pairs move across each other. As you can see here, the difference in the shape by 15 degrees. This the planes of the two, if this is represent an X letter, you can see here the two arms of the X letter as sort of wider by 15 degrees. And this is to show you that the total structure, the salt bridges are present, and here in the R structure, the relaxed state, all the salt bridges are ruptured or broken. T state has lower substrate affinity to the substrate oxygen. The T form has lower oxygen affinity, while the R form has high oxygen affinity. So this R form is suitable for binding oxygen. Each hemoglobin molecule binds 4 molecules of oxygen. So there is 1 molecule of oxygen for each subunit of the hemoglobin. Oxygen binds to here more rapidly if other oxygen molecules are already bound. So the binding of the first oxygen molecule will be tough, the binding of the second will be easier, the binding of the third and fourth will be much easier compared to binding of the first molecule of oxygen, because subsequent binding of oxygen requires rupturing of fewer salts. When the first oxygen is entering the hemoglobin molecule, it will have be faced with rupturing, or will have the task of breaking all the present salt bridges. And when they are sequentially being broken, binding of subsequent oxygen molecules will be much easier. As you can see here, the straight lines represent strong bonds, electrostatic bonds, with binding with the ferrous oxygen. This one here is broken, and those one are weakened with binding of more subsequent oxygen. This one here is broken, now theirs are weak, and so on, until all the electrostatic bonds have been broken. We need to come across a term or a concept of partial pressure of a gas. Partial pressure of a gas is a pressure that a gas in a mixture of gases would exert if it occupies the same volume at a mixture at the same temperature. So if gas A will occupy this volume, if gas B, its pressure at that time is 10, if gas B occupies this volume, the same volume, its pressure is 5. If they are in a mixture, their the partial pressure of each will be represented in the mixture, so it will be 15, whereas a 5 is the partial pressure of gas B, and 10 is the partial pressure of gas A. Dalton's law states that the total pressure of a mixture of gases is equal to the sum of partial pressures of each individual gas in the mixture, which we have just explained. The mathematical expression is simple, is that partial pressure is total equals partial pressure of the individual gases in the mixture. We have what we call P50, or the partial pressure of oxygen 50 is a measure of oxygen concentration. It is the partial pressure of oxygen that helps saturate hemoglobin molecule. So it is a partial pressure of oxygen at which 50% of the hemoglobin molecule will be saturated. So if we plot the pressure from 0 to 160 millimeter mercury, partial pressure of oxygen, and here we have hemoglobin saturation from 0 to 100, partial pressure that saturates half of the molecule of hemoglobin is called the partial pressure of oxygen. The concept of partial pressure of oxygen is important for the function, for example, of the hemoglobin. Partial pressure P50 for hemoglobin A for the adult hemoglobin is 26 millimeter mercury, while that of hemoglobin F, the fetal hemoglobin, is 20. This difference is quite important. 26 and 20, as you can see here, shown in red is our adult hemoglobin, and shown in blue is the fetal hemoglobin. They have different partial pressure of oxygen. That of hemoglobin is less than adult. It's important for extraction of hemoglobin of oxygen from the material circulation by the fetal circulation. If this difference between the two pressures is absent or abolished, the fetus cannot take oxygen from its muscle. Hemoglobin and myoglobin have what we call dissociation curves. These curves illustrate the relationship between the partial pressure of oxygen and the quantity of bound oxygen, that is the saturation, a relationship between partial pressure and saturation. And they explain how hemoglobin and myoglobin are suited to their function. We are going to see that in a minute. So these are the two curves. The partial pressure in the x-axis here in millimeter of mercury, and the y-axis here represents percent saturation by oxygen of hemoglobin or myoglobin. And in blue here is the dissociation curve of hemoglobin, and in black here is the dissociation curve of myoglobin. As you can see here, hemoglobin higher up here represent the area where where hemoglobin is oxygenated in the lungs, and lower down here represents the area in the tissues, in the peripheral tissues, where hemoglobin will have to unload or to give this oxygen to the tissues. Myoglobin dissociation curve is hyperbolic. Myoglobin releases oxygen at partial pressure of oxygen that are less than 5 millimeters of mercury. So myoglobin will not release. It is stored oxygen unless the pressure in the muscle is less than 5 millimeters of mercury, and that will occur in muscles that undergo strenuous exercise, which will allow continuation of activity. So it will release this oxygen at very low oxygen saturation levels of less than 5 millimeters mercury. So myoglobin is suited for storage rather than transport. This is a hyperbolic curve. As you can see here, it will not release oxygen unless it is very the saturation is very low. It can take up oxygen at partial pressure of oxygen at 20 or less even. In comparison, The dissociation curve of hemoglobin is sigmoid in shape. It loads up oxygen at partial pressure of the lungs at very high pressure. Unlike myoglobin can unload, as you can see here. Myoglobin can still take up at 80, at 60, at 40, at 20, but hemoglobin loads up at 100 millimeter of mercury at very high levels of partial pressure of oxygen that occurs, of course, in the lungs. It unloads or it releases this oxygen at lower partial pressure of oxygen at the level of tissues that is about 40 millimeter of mercury. Myoglobin will not release this oxygen unless it is 5 or less, but hemoglobin releases it at about 40, and thus hemoglobin is more suited for transport. It doesn't need the tissue to have very low oxygen, for example, around 5, like myoglobin, to release this oxygen. Hemoglobin is also suited for transport because it is a tetrahedral structure. It has 4 molecules, so it's suited for transport. It can take 4 oxygen molecules instead of 1 molecule. And you can comparison, for example, a motorcycle can unload, for example, can load 1 passenger, but a car, suburban car, for example, can take 4 passengers. And this is an advantage for hemoglobin, which makes it more suitable for transport. This is a sigmoid shape of hemoglobin. Oxygen occurs at very high levels of oxygen in the lungs, and at about 40 or so, it will start to release this oxygen to the tissues. We have what we call right shift and left shift regarding hemoglobin dissociation curve. Right shift is movement is to your right here in the curve. So this is this is the position. The blue one is the dissociation curve. Shown in red is right shift, so it moves to the right, and shown in green is the left shift, so it moves to the left. Both the movements of forces across the x-axis. Right shift means more oxygen delivery. It will occur at more acidic pH, at more higher partial pressure of carbon dioxide, in the presence of 2,3-bisphosphoglycerate molecule, the glycolytic intermediate, and in there is temperatures higher. And this is suitable because in the tissues, if they are metabolizing tissues, there is production of carbon dioxide, and the acid will be the proton will be also produced, leading to higher higher pH. So sorry, lower pH, acidic pH, and production of carbon dioxide as the level of metabolizing tissues. This will lead to a turning right or shifting right of the dissociation curve, leading to more release of oxygen. While if there is alkaline pH, a higher pH, and low carbon dioxide, low 2,3-bisphosphoglycerate, low temperature, or if there is hemoglobin F and methylprotein, it will be shifting left of the hemoglobin dissociation curve with less oxygen delivery on this side. So less oxygen delivery means it will release oxygen at much higher saturations. It will be similar to myoglobin. What is bisphosphoglycerate? This production allows glycolysis to continue when the need for ATP is minimum in the disease. It promotes oxygen release by stabilizing the protein structure of deoxyhemoglobin. So it binds here in the core of the hemoglobin molecule, stabilizing the oxyhemoglobin molecule. Proton and carbon dioxide transport. So as we said, hemoglobin does not only transport oxygen, it also transport carbon dioxide as well as proton. In addition to oxygen transport from the lungs to peripheral tissues, hemoglobin also transports carbon dioxide, a byproduct of respiration, and protons from tissues to the lung. So it is in reverse transport. How or what is the form of carbon dioxide transport? transport either as carbonate or as a bicarbonate. Carbonate accounts for 50% of the transported carbon dioxide in venous blood, while bicarbonate accounts for the rest. This is the carbonate group, and this is the equation by which carbon dioxide forms bicarbonate and vice versa. We'll discuss it in detail as we come to the Bohr effect. Remember that carbon dioxide occurs in two forms, in an aqueous form in the blood and as a gas in lung space. How is proton transported? The oxyhemoglobin binds approximately 0.6 proton ions or hydrogen ions, protons or hydrogen ions for each oxygen molecule released. So the tetrameric hemoglobin binds about 2.4 proteins for 4 molecules of oxygen. So roughly it is around 1 to 2, 1 proton for each 2 oxygen molecules released. The oxyhemoglobin so acts as a buffer by binding protons and delivering them to the lungs, because it takes those protons from the tissues and transport them to the lung. When we reduce the level of protons, we are altering pH of the pH of the tissues. At low pH, at acidic pH of the peripheral tissues, aided by carbonation, stabilizes the T state, the total state, and enhances oxygen delivery. As we said, total state has less affinity for oxygen, so it's less likely to bind to that oxygen if we release it for the tissue. So now we come to Bohr effect. Bohr effect explains or how the changes in pH and carbon dioxide concentration influence hemoglobin oxygen binding affinity, the shifting right and left shift. The Bohr effect is dependent upon cooperative interaction between the 4 halves of hemoglobin. Myoglobin being a monomer, of course, does not exhibit Bohr effect. Bohr effect is crucial for efficient oxygen delivery to tissues and oxygen uptake in the lungs. So it is at the level of upload of oxygen in the lung and at the level of downloading or releasing oxygen at the level of the tissues. Bohr is needed at both sides. Bohr effect states that oxygen binding affinity is inversely related to both acidity and concentration of carbon dioxide. The higher the acidity, the higher the concentration of carbon dioxide, the less the binding affinity of oxygen by hemoglobin and vice versa. So a decrease in pH due to an increase in protons or hydrogen ions or an increase in carbon dioxide reduces hemoglobin affinity for oxygen, so it will promote release of oxygen from the myoglobin molecule to the tissue. An increase in pH or a decrease in protons or a decrease in carbon dioxide enhances oxygen binding to hemoglobin, so the hemoglobin molecule is more likely to bind oxygen rather than to release it, and this is most likely in the level of the lung. The mechanism of Bohr effect is quite simple. You discuss it at the level of the tissue and at the level of the lung, where the two factors function. At tissue level, you need oxygen release. At tissue level, you want your hemoglobin to release its load of oxygen to give it to the metabolizing tissues. Actively metabolizing tissues, of course, produce carbon dioxide and proton from carbonic acid breakdown and lactic acid. Increased hydrogen ion binds to hemoglobin. It stabilizes the total state, which has low oxygen affinity. So now hemoglobin is changed into total state, which has low oxygen affinity, so it is less strongly bound to its oxygen. It has a tendency to release it. So this oxygen will be released and it will be available of tissues. So the buffer is actually the deoxyhemoglobin. So at the level of the tissue or venous blood, tissues produce carbon dioxide and proton. Carbon dioxide combines with water in the presence of carbonic anhydrase enzyme to form carbonic acid. Carbonic acid spontaneously dissolves into bicarbonate and hydrogen ion or proton. Proton here has a crucial role. It stabilizes the total state of hemoglobin, which promotes oxygen release to tissues. So the overall effect is that oxygen is released from hemoglobin and right shifting of the hemoglobin dissociation curve. On the other hand, in the lungs, you need oxygen binding. Oxygen is present. You need to upload oxygen into the hemoglobin molecule. We need also to exhale carbon dioxide. So in the lungs, carbon dioxide is exhaled, reducing proton concentration, increasing pH. What happens to the curve? Hemoglobin curve shifts to, and the hemoglobin molecule itself moves from T state to the R state, which has high oxygen affinity and starts to take up oxygen. Oxygen binds more efficiently to hemoglobin to be transported later on in the body. So in the lungs, the same equation we have just mentioned, it will be reversed. We have high oxygen concentration in the lungs, so oxygen uptake by the hemoglobin releases protons that have been taken up earlier on from the tissues. These protons will be released in the lungs. Protons will bind with bicarbonate, spontaneously forming carbonic acid, and bicarbonic anhydrase, it will form, it will be dehydration of the carbonic acid, water will be removed, and carbon dioxide is formed. This carbon dioxide will be expelled, and the low hydrogen concentration and the high pH will shift hemoglobin to the R state, which will increase its affinity, leading to uploading of oxygen into the hemoglobin. And this is the combined effect or Bohr effect. Carbon dioxide and water, formation of bicarbonate and proton, hemoglobin acting as a buffer, taking up the proton, being in the R state, to T state, releasing oxygen to the peripheral tissues. In the lungs, the opposite occurs, where the carbon dioxide is formed and expelled, and proton is used to form carbonic acid. Physiological significance of Bohr effect is that enhanced oxygen delivery to metabolizing tissues, enhanced oxygen loading in the lungs, in exercise and hypoxia and high altitude. There is high production of lactic acid and carbon dioxide. So the effects here enhances oxygen unloading via the Bohr effect. So it will provide oxygen for the exercising tissues despite hypoxia and high altitude. Fetal hemoglobin has weaker Bohr effects than hemoglobin A, and this allows a fetus to retain oxygen more efficiently from the maternal blood. Hemoglobin variants. Numerous mutant hemoglobins have been identified. Mutations can potentially affect the biologic function. More than 800 mutant hemoglobins are rare and benign, so they have no clinical sequence. So these mutant forms of hemoglobin can either be benign without any clinical significance, not affecting the function of hemoglobin and not typically appearing in any way, or it can affect the function and have certain consequences. So the question is, for you, is to write down 6 examples of mutant hemoglobins which have no clinical sequence and describe how are they structurally different from normal hemoglobin. One of the hemoglobin variants is methemoglobin, in which the heme ion is ferric instead of ferrous. We said the function of hemoglobin and myoglobin, both of them needs ion to be in a ferrous state. However, in this ferric state, it's now called methemoglobin. It results from oxidation, for example, dioxin, such as sulfonamides. It can be hereditary, hemoglobin M, in which histidine Fm, histidine is replaced by tyrosine. So this polar amino acid is replaced by an unpolar amino acid. Aromatic amino acid. Reduced activity of methemoglobin, of the enzyme methemoglobin reductase. The enzyme that is supposed to reduce ferric into ferrous ion. So the whole function, which is dependent on ferrous hemoglobin, is entire. Hemoglobin S, an abnormal variant of hemoglobin caused by mutation in hemoglobin beta chain on chromosome 11. Particularly, it is a single point mutation where by surface glutamate, a polar amino acid, is replaced by valine, which is a non-polar amino acid at position 6 of the beta chain of hemoglobin. So this is position 6. This is the codons and anticodons, and this is our translated amino acid sequence. We have valine 1, 2, 3, 4, 5, 6. This position normally in a beta chain is a glutamate. In hemoglobin S, the mutation leads to replacing this glutamate by valine. What is the consequence of this mutation? This creates a hydrophobic sticky patch on both oxyhemoglobin S and deoxyhemoglobin S. Both deoxyhemoglobin A and deoxyhemoglobin S have a complementary patch, so it affects the overall three-dimensional structure of hemoglobin. Normally, it is compact like this. The surface is smooth, the two alphas and the two betas. When hemoglobin is sickled, hemoglobin S has this sticky patch, this part that is sticking outside the plane of the molecule, and it is also present in the oxyhemoglobin S. So in hemoglobin S, whether oxygenated or deoxygenated, contains this sticky patch, shown here in black. While the oxyhemoglobin A, the oxygenated hemoglobin A, and deoxyhemoglobin S contain a complementary site for attachment of that patch called the complementary patch. The sticky patch and the complementary patch stick or each other like a lock and key. So the patch will stick into the complementary patch. This is serious because when they stick one to the next, this will lead to polymerization of the hemoglobin molecule. Hemoglobin molecule is supposed to be soluble. Each hemoglobin molecule is supposed to be alone, an individual floating within the medium of the red blood cell. It should not be linked to each other in a polymer or a fiber like this. So at low partial pressure of oxygen, deoxyhemoglobin S can polymerize to form long insoluble fibers, which distort the shape of the RBC in the characteristic sickle shape, which causes spices in the splenic sinusoids and occlusion of small vessels. So this is the normal biconcave disc of the red blood cell. When the hemoglobin S at low oxygen polymerize and forms fibers, will be stuck into one side of the cell. If we change the shape of the cell into a sickle shape instead of this normal biconcave disc, it is like to a sickle, so it is called sickle cell or sickle red blood cell. What is serious about this change of shape? This will make it more likely to be lysed in the splenic sinusoids, and it will more likely to occlude small blood vessels. It will be stuck here and will include small blood vessels, and will cut supply from the distant tissues. Hemoglobin S is inherited in autosomal recessive manner. So 25% of children will be affected, 25% will be unaffected, and 50% will be carriers. Homozygous hemoglobin SS is called sickle cell anemia, while heterozygous hemoglobin AS is called sickle cell trait. These terms, we need to differentiate between them: sickle cell disease, sickle cell anemia, and sickle cell trait. Sickle cell disease, the phenotype includes hemoglobin SS, hemoglobin SC, and hemoglobin S beta thalassemia. So it will have one hemoglobin that is either the two hemoglobin are S hemoglobin, sickle, so both of the beta chains have the mutant the mutation, the point mutation of sickle cell disease, or one hemoglobin chain is S hemoglobin and the second is C, or one is sickle and the other is thalassemia. So both of chains will be mutant. The severity is moderate to severe and presenting as anemia, painful crisis, and organ damage. Sickle cell anemia specifically denotes hemoglobin SS. So sickle cell anemia is a subtype, or it is included within the entity of sickle cell disease. This one here. It's the most severe and it has frequent with vaso-occlusive crisis and sickle cell trait represents a normal chain and an abnormal S chain, so it is carrier state. It has mild or non-severity and usually asymptomatic, and this it is triggered with their complications. Another hemoglobinopathy is thalassemia, ورقين البحر الأبيض المتوسط, a group of inherited blood disorders characterized by reduced or absent production of globin chain of hemoglobin. So like sickle cell, the globin chain is also affected. However, thalassemia can affect both alpha and beta chains. So we have alpha thalassemia, which is caused by deletions or mutations in genes hemoglobin A1 and or A2 that cause for the F1 and F2 chains of hemoglobin, or it could be a beta thalassemia with mutations in hemoglobin B gene, F2B gene, which cause for the beta chain of hemoglobin. Alpha thalassemia can be a silent carrier where when alpha is affected, without any symptom, and can proceed in severity up to loss of all four chains, which will result in a serious condition of hydrocephalus with death in utero. Beta thalassemia, there is beta thalassemia minor, beta thalassemia intermediate, and beta thalassemia major, ranging in phenotype from mild anemia up to severe anemia, which requires regular transfusion. An exercise for you is to compare and contrast hemoglobin and hemoglobin according to these items. And this will be all. Thank you very much.